Good morning, all. I want to start by echoing what Sam said about the competition. It's an accuracy competition, not a speed competition, and so I'm going to talk about what hopefully can make all of you a little bit more accurate. So why are we here? Board planning. As I said, board planning really is it's like a roadmap. We know where we need to end, but the board plan is going to tell you how to get from where we want to start to where we want to end. In the past, board planning has been considered very complicated. It takes time, and in some cases, people think it's unnecessary. Now, it could be all of these things, but I'm going to try to see if I can demystify board planning a little bit. But I'll start out by talking about why we should board plan. Having said that, everyone plans. It might be as informal as we're going to enter over here, we're going to come out over there somewhere, and we'll stay at about 4 feet. Traditionally, probably does not count for a board plan, but that's what a lot of people do. There's nothing in the way. I've been drilling for 25 years. That's all I need. Some people go a step further. We can use the transmitter to take readings of the terrain, get a little bit of an idea of what the terrain's doing. So now at least I have some idea of what the slopes is that I'm trying to follow. We have more comprehensive board planning, which typically involves a survey of some sort. And then we go all the way to a detailed survey, engineered bore with hydrofracture and load calculations, typically reserved for some of those longer bores Sam was talking about. I'm going to be talking mostly about sort of a comprehensive survey, and we'll talk about what comes out of that in terms of a rod by rod plan. So why are most bores, and I'll actually ask the room, if there's some contractors here, which ones of you bore plan somewhat regularly or maybe even not at all? No hands. Doesn't necessarily surprise me, but boring, it does take time to plan a bore, and it does require a survey. Traditionally, survey means we got to find a guy who knows how to operate the GPS. We got to pay him some money, and he'll show up in about 5 weeks, and we'll get a survey. At that point, we can start creating a plan. A lot of the jobs just don't have the budget for a detailed plan, and that's fair, especially on the fiber side of things. What's being paid for fiber really doesn't warrant much of an engineering effort. And one thing that I've heard in various versions, well, I'm not really going to go that deep. I'm only going a few hundred feet. I don't really need a plan. And so that's fair. I'm not a driller. There's a lot of people in this room that have put a lot of pipe in the ground. I'm going to talk a little bit about how we can maybe make that a little easier, how we can make you safer, potentially more accurate. We'll talk a little bit about depth. So in our world, which is walkover locating, depth is always referenced on the surface. When we say something is at a 5 feet depth, that means right where I'm standing, something is 5 feet below me. Now, what that means, however, since we're always talking about where I happen to be standing, it's very difficult to say anything about depth changes if I don't know what the terrain is doing. Let's take a look at an example. So I'm drilling at 0% pitch, and I have some sort of a depth. I'm going to drill a couple of rods at 0%. And the question is, what's my depth going to be? In most cases, it's going to be pretty close to what it was, except when the terrain does this or that. So my depth, again, because it's a reference off the surface, really now has much more to do with the terrain than it has to do with what I was doing on the ground. So drilling at level pitch doesn't necessarily guarantee that I'm going to maintain my depth, unless again the ground is flat. another way to maybe illustrate this is that I'm coming up on this utility. I've done my rise over run calculations, and I'm doing quite fine. I'm going to go above this as I plan to do. I know what the depth of this gas is, and again, unless the ground does this, then my depth, which was adequate in the first example, really isn't so good in the second. Again, all I'm arguing is that without knowing what the terrain is doing, it's very difficult to say anything about depth. When we don't have a plan, we are more reacting than being proactive. Those changes in the terrain I was talking about, they often dictate what I can do. There was a dip that it didn't account for, so now I got to do something to account for that. Navigating becomes a lot more complicated. A decision I made a couple of rods ago. So I made a decision on rod 6 to come down to miss a utility that's coming up. Now that decision actually means that what I was thinking that I might be able to do over there just no longer works. Because that decision has an impact on something going on. Now I don't know that, I won't know that until I get there. So once I get over there, we're going to have to pull back potentially and reassess what we can do. Another way of saying that is that the entire bore and everything that you have to cross really isn't being accounted for when you don't have a plan. And finally, because of this pullback issue, trying to figure out what do we do now, we sometimes end up spending more time. Here's a few other things that having a plan reveals. What the crew has been asked to do really isn't achievable. Maybe I'll do this. What that means is that many times a crew has been asked to, we need you to be at some depth and level right here, and we need you to set the machine up over there. Well, that may or may not work. Sometimes the setback distance just isn't enough. And this is a variation of what I already said, is that by choosing to go above a utility, then it may be impossible to go below the second one because we don't have enough clearance. If you have a plan, given where all the utilities and the location is, it might actually make sense to drill from the other direction. We had intended to drill north-south. It might make more sense to go south-north. And finally, once you have a plan, it is probably one of the best tools you can have to talk to engineers or other stakeholders about, this is what we're trying to do, and here's why it's going to be complicated. And if we are allowed to go deeper, allowed to go shallower, allowed to move back a little bit, things are going to become a lot simpler. Another benefits, again, you have the entire bore in front of you. Utility locations, as we see in the picture there on the right, that's what the locator is looking at. He's looking at paint marks, he's looking at potholes, he's looking at utilities, and he probably can only realistically account for 2 or 3 at a time. Anything beyond that, we'll sort of have to deal with once we get there. The other benefit is that we can do some what ifs. Is that, again, is it better to go below these 2 utilities and then above the other one, or the other way around, assuming that that's allowable. Having a bore plan is a great training tool. It allows those less experienced crews to actually have better discussions about what is and isn't possible, how might we want to do this. And again, by changing the plan, it becomes very obvious very quickly, well, that's not going to work, we've got to try something different. And all of this is being done before you have 4 or 5 guys plus machinery in the field waiting to figure out what happens next. And ultimately, we end up with a better product because we have thought through all the options. We may have planned this thing a few times, and we come up with what's going to work the best. And we're going to end up with something that may look like this. So transitioning from that picture, where utilities are represented as marks on the ground, to something that looks more like this, where we now actually have those utilities and we have a bore path, and we can be fairly well assured that we're going to miss them with adequate clearance. A little bit about other sort of ancillary benefits. We do get better productivity because we're not spending time rethinking decisions. We do have a roadmap, which is literally be at that pitch and that depth on rod 7. That allows the pilot board to be installed a lot more smoothly, which ultimately then ends up with a much easier pullback. Now, we're not going to wear our drill pipe as much as we do if we don't have to do emergency steering. And if we do have to redirect, which does happen, we now have a plan. We sort of know what we're aiming for. We know that a few rods out, we need to be at this pitch and that depth, and we have a way to get there. Now, potentially, we do have less fuel because we're spending less time. The machine is not working as hard during the pullback because we have a plan. And again, back to the communication tool, if we have a plan, it's a way to have more fruitful discussions with either clients or other stakeholders. I'm going to talk a little bit about the TeraTrak. Again, question, is this the first time you guys have seen or heard of this thing? Okay, I guess that's good news. What this was meant to be, this was meant to simplify the act of bore planning. The biggest issue with bore planning typically has been the fact that surveying is expensive and most people don't have the time or the money to survey. So we built this tool which basically integrates the bore planning and the surveying into the same tool. It really is a measuring wheel, except it's a little bit more advanced than the ones you typically use. So what we do is as you roll across the terrain, we're continually measuring angles. So as we go uphill, we're measuring those angles. As we start coming down, we measure that angle. And so ultimately, as you walk the bore path, you end up with a pretty accurate depiction of what the elevation is. And as you can see, we're saying plus or minus 2 inches over 500 feet. That's not as accurate as you could get with actual survey, but if I have time, we can talk about the differences between what we do and what the survey does, because having continuous terrain is, I would argue, actually more accurate than what you get out of a survey. Getting into kind of the nitty-gritty of what it does. So as we're rotating, we're taking readings every 0.4 inches, give or take, and we're combining the distance traveled with the angles, and out of that comes the terrain. Of course, we have proprietary algorithms. That's an engineering way of saying cool stuff. And as you'll see in some of the animations, we're actually creating the path in real time as you cross over the terrain. And we do have understanding that the terrain that you guys are crossing can be rugged, can be difficult. So we've built in a speed gauge, which basically tells you the speed by which you need to move to get the best readings. Hopefully, we've been able to design it such that it is so simple that anyone can use it. I talked about the setback distances. It fairly quickly allows you to see, can I do what I have been asked to do? And if the answer is yes, then it gives you the answer of how can I do it. If we need to just get from A to B, I got this one utility, and then I got the other one, and I got some terrain changes in between. How do I deal with that? So we can fairly easily get you from A to B. But ultimately, we can also give you the entire bore path. So I'll walk through a few examples here. So what we're looking at, this is just to show you kind of what this looks like. So this is what the operator is looking at while they're walking the path, starting going up a hill. As you can see at the top, we're about 30, 40 feet into this thing. We're going to pause. This is our first utility. And so we've potholed it. We know its depth. Looks like it's gas. It's at a depth of 4 feet, looks like. And we can give it diameter, we can give it a clearance, and here's our utility. And at that point, we would continue, and we'll move on to the next one. 2-point calculator. Again, this is not in the context of a full bore plan. This is just how do I get from A to B. Oops. Here's the situation. I haven't been bore planning at all, but I just crossed this water, and I got this gas I have to go below. How do I go from where I am and make sure that I can go underneath that gas? I know this is stuff you guys do all the time, and you don't need a bore plan to do it, but there's probably situations where you wish you'd had some way of helping you to do the math. And that's in essence what we're doing. We're doing the math for you. So in this particular case, I just took a depth reading from my locator. I'm doing a 2-point calculation. Looking at my locator, I was at a depth of 3 feet. I'm coming down at, no, drilling level, but I want to end up at a depth of 7 feet and be level. So I'm walking from my drill head towards where I need to be, and I'm drawing this bore path. The fact that it's red indicates that I'm overbending something. At some point in time, it'll turn blue, indicating that I now have what we call a valid bore plan. Now, 2 things may be true. I may have reached my pipe, or I may have had to go further than the pipe, which means that I may not have had enough room to get below the gas, given what the situation was. So it will reveal to you fairly easily, can I do what I'm trying to do? And if the answer is yes, I have a bore plan. As you can see, this is a short 5-rod plan. And again, there's nothing magical about this particular plan, and this happens to be a fairly simple thing to solve. But just to illustrate how quickly and how easily you get the results out of this thing. Setback, again, I need to be level and some depth here. Where do I set up the machine? We're gonna basically, this is a little bit counterintuitive. I'm drilling from that direction, which means I'm drilling this way. So I know right here where I'm standing, this is where I want to be at my depth. Question is, where do I set up the rig? Again, we're drilling that direction. I'm going to actually walk towards my entry. So I'm going to create a setback calculation. And we're going to enter some depth. Some kind person told us that I need to be at some depth. And that is 5 feet, and we want to be level. My rack angle is 24%, and now I'm walking towards, as you can see, actually the line is moving in that direction. We're walking towards where the machine is going to be set up. When this turns blue, that would be the shortest distance that I can safely go from entry to where my depth and pitch was meant to be, and in this case looks like about 4 rods worth. Again, this is something you guys do all the time and don't need a bore plan, but there are situations where there might be utilities in the way, there might be elevation changes, and back to my comment earlier about we don't really know what depth means unless we know what elevation changes mean. Doing the math is one thing, doing the math, taking the terrain into account is potentially another. So what do we get out of a bore plan? So traditionally, bore plan basically means you have a rod number, you have some sort of a pitch, and you have some sort of a depth. What we do ask you is basically, at this particular point, do you know what the pitch is going to be? Many times you may not know what the pitch is. If you do know that you're going below a creek, for example, you have to be at a depth of 8 feet below the bottom of the creek, and you do want to be level, you can enter that. Typically speaking, it's better to allow the program to calculate those pitches for you. But we ask you, do you know what your pitch is? That'd be the desired pitch. Do you know what your desired depth's going to be? And how much are you willing to bend the rod? Now again, that depends on either the rod itself, depends on the product that we're pulling back. But once we know these very basic things, waypoints, which is basically I want to, at this particular point, I want to be at this depth and potentially that pitch. That's basically all we need from you. A depth, maybe a pitch, an entry and an exit. And if you give us those things, we can come up with a plan. Now, it may not be a valid plan. Valid plan meaning what you asked us to do is exceeding typically bend radius that you allowed us. So if we're drilling, let's say we're using a mud motor or we're pulling in steel, what we can bend is significantly different than what we can do when we're doing plastic. So you have to allow potentially for a lot longer entry plan than you normally do because we can't bend as much, or coming out of the ground on the other side is going to take us longer to get out of the ground. All these things is what the board plan takes into account, and it'll tell you fairly quickly you're actually going to need 100 more feet because the fact that you're bending so slowly, what you've been asked to do is just not going to fit in the envelope that you've been given. Talk a little bit about remote integration. For those of you who use our system, you're looking at an Aurora display. In this particular case, we've taken the board plan that came from an R1 and transferred it to the Aurora. That then allows the operator, in addition to the normal pitch and depth and other things that they see, it allows them to view the board plan and then log their actuals against the board plan. So now we have not only where are we supposed to be, we also have where we are. That makes the decisions on how to redirect a lot simpler. I have a picture of where I need to be. I know exactly what I need to do. Again, allowing the decision to become that much simpler. I have a lot more information at my fingertips than I typically do. Also, just as important, I have a view of where my utilities are. I know as the operator, because I can see it on the screen, right there at the top it says 9'7". That is the distance to my nearest utility. So I know that I got about a rod, if I'm using tempered rods, I got about a rod until I cross this utility. I can verify with my locator. He may be 500 feet up. Looks like we're about 10 feet from that utility. Is that correct? Yep, okay. I'm showing this depth. Yep, I'm seeing that on my locator. Communication tool where both people have a lot more information than they typically do. Question we asked earlier. So how do we answer this question? Well, typically today I take a look at it and I say, it looks like about a foot. And I've asked a lot of people this. It's notoriously difficult to look 200 feet out and say, yeah, that feels like 2 feet. Typically, we don't get it right. So built into the R1, we actually have measurement mode. So if we do really want to know, I'm dragging my finger across the screen and I'm seeing what my elevations are. They're to the top, the second number from the right. And or if I really want to measure, I have these 2 points of interest. And for some reason, it's important for me to know exactly what's going on there. I use measurement mode, and we can see that there's an elevation difference of a little over 14 feet over a 42-foot distance. Now that particular slope is negative 36. So without doing any kind of board planning per se, but if I was trying to follow that slope or maintain depth, I now know that I would have to be at about a negative 35% pitch to maintain that. Now this is the example board that we put into the app. It's a manufactured board to make some of these points. That elevation difference from the top of the hill to the bottom is about 30 feet. Now those things obviously do happen, but Back to answering the depth question and the terrain question. Once you've taken the survey, you now know everything you need to know about the terrain. And you can, as I sometimes like to say, interrogate the terrain. Well, what about the difference between my entry and exit? What about that hill? What about that little dip by the road? What do I need to do in terms of make sure that I maintain depth? Again, that's all independent of bore planning. That's just knowing what the terrain is. So even if you don't do any bore planning, having this kind of information is eminently useful. Talk a little bit about accuracy, because I was talking about this thing potentially being more accurate than a survey. And so that's maybe a topic for a different discussion. But while we were developing this, we obviously did a lot of testing. So we had 8 different sites representing both different terrain and different elevations, and we surveyed those pretty extensively. And then we ran multiple tests using the R1 against those already surveyed and known terrains. This is a picture of a hill, Lake Tapps, which is a little bit south of Seattle, about 20 minutes south of where we are, DCI in Kent, Washington. This was a 900-foot long run, elevation drop of about 82.5 feet. So we recorded 35 survey points. So basically every 25 feet we took a survey. And in one particular test, I think we ran probably 30 tests on this particular hill. The one I'm sharing here, we did 3 runs. The elevation differences were 82.66, 82.6, and 82.63. So that's what the R1 said, when 82.53 was the actual survey elevation difference. So at that point, we're a little less than actually a little over an inch in an elevation difference between what the survey said and what we came up with. Second test was done in Oklahoma. This represents a survey compared to what the R1 did. The blue dots, I don't know how well you can see those, the blue dots are actually the survey points, and the orange line is the R1 path. In this particular case, they did 17 survey points. The average error was a little over half an inch. Now, I will say, there's definitely situations where the R1's not going to work. There's through heavy brush, through very coarse cobble. But probably for most of the terrain you guys are dealing with, it actually should work pretty well, and it will give you the accuracy that you need.